Okay, so today we're going to be talking a little bit about stereochemistry. So, this is another concept in OChem that I think a lot of people start to get a little confused about when compared to Gen Chem. So, let's just kind of get into the basic idea of stereochemistry. So, long story short, stereochemistry is just how each constituent of a molecule interacts spatially. So what does that really mean? So we know if we have an sp3 molecule, so let's just kind of draw this. The end here we have C, and then we know that carbon has three hydrogens coming off that and another carbon. So if we just kind of zoom in here on this one carbon, like looking into that, we have this carbon here would be attached to hydrogen, 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 and then carbon. So we know three-dimensionally this sp3 molecule it's not just flat. It's really it would be tetrahedral, so it would be more like I can't really draw this in 3D. It's kind of hard to explain. But basically, if you think of this molecule as a 3D object, one of these hydrogens here, this, for example, the one I circle here would be facing away from you. This one would be going away from you. This one would start be a little more close to you, and this one would be going to the right, but still somewhat close to you. So the way we draw that, so when we draw a bond line structure, we can't draw it all in 3D because that's just too much. That's too hard to explain. So we do a wedge, which I will be drawing here, and a dash. So that doesn't look good actually. So and a dash. So that basically we're just gonna assume these are methyl. So let's just do CH3 and CH3. So essentially this wedge, let's see if we can fill that in. Okay, it doesn't work. It's my first time doing this. So let's just assume this wedge here. This means that this carbon, this methyl group, is coming towards me. I'm looking at it, it's coming towards me. If you think of one of those 3D bond line connection tools, like it's if your teacher's ever shown you that, where it's basically balls connected with rods. This methyl group here would be coming towards me. This carbon would be looking at me. The face of this is looking at me. And then so this carbon here with the dash, it's facing away from me. So essentially if we're looking at like a top and down, if my eye was looking here, top down, I'm looking like this, looking down on this molecule, we would have, now let's draw this. Let's just say this is the methyl, or not the methyl. This is the main bond line. It's going like this. I'm looking down on it. So this carbon here would be this one, which I've circled, would be going like this, going away, and then this one would be coming towards me. So these really, long story short, these are facing opposite directions. These carbons are going different directions. And it's very hard to explain that when drawing in 2D, which is why we have a three-dimensional tool or a 2D tool to visualize a 3D molecule, which is called a Newman's projection. So let's just draw a molecule here. Let's say we have this, there's a wedge, there's CH3 once again, and then on this we have, let's say we have bromine. So now, looking at this molecule, we're going to have me looking at the 3D model. I'm going to be looking at it this way. So the front of the Newman's projection will be here. Let's do a little 1 and then 2 here. So now let's draw the Newman projection. It looks something like this. So excuse my circle, but we have this, which would be the front, and here is the back of A new rejection. Let's get rid of this title. So the front, let's look. So the front molecule, this one here, which I'm drawing in, that is really this carbon here, which I'm going to be drawing in like here. So what do we have attached to this carbon? We have one on the wedge. There is methyl. Then we have an ethyl group coming off it here, and another ethyl group which has bromine. So with the wedge, a wedge is always, I'm just going to write this down. Easy way to think of it, wedge will be right and dash will be left when we're drawing a Newman projection. So what does that really mean? So on the right side, we have the wedge. So we have CH3. Just easy, you can fill that in. And you might say, okay, well, we don't have a dash here. We only have a wedge, and we have the two straight lines, but where's the dash? So we know this, if we don't have it indicated, we can just assume there is a hydrogen here. So let's put the hydrogen there. And then what's the other line that's going the opposite way? We have an ethyl group, so it would be looking something like this, like that. So that's the front side of the Newman projection. So let's look at the back. We have the second carbon. So once again, we can assume the wedge would be hydrogen. So let's fill in hydrogen here. And what's on the dash? We have bromine. And then the last molecule, we have another CH3 methyl group. So that's how we can visualize this molecule here. Let's kind of just get rid of the clutter again. Oh, didn't mean to do that. There's a lot going on that I drew. So that's how we can really visualize the 3D, or not 3D, the 2D molecule in 3D, which is very hard to kind of wrap your head around. So you might be thinking, why would I need to know this? Like, I understand, if you might understand a wedge, dash, I get that, but why don't you know this? Because later on in OChem, and especially OChem 2, we have reactions that can only proceed based on what the stereochemistry, which is like the 3D arrangement, based on, so there's reactions that can only occur based on the spatial arrangement of the molecules in the reaction. So in the future, there will be reactions where if essentially if this bromine had, or I guess not the bromine, but let's just think of it, there will be reactions where the stereochemistry will be changed due to reaction. So that's basically why you need to know this. So that's how you draw the Newman projection. And another thing we can get into is drawing the chair flip of hexane. So let's just draw hexane molecule here. So one thing that I had no idea what was going on when I first took OChem 1, why is my thing not working, is what the heck is this thing? So we look at this, and this is, you know, the chair conformation of the molecule. So I did not understand, it took me a long time to understand, this here, this chair flip is what we're calling it, let's just, or just chair conformation. Conformation, actually. This is OChem, this is not spelling class. So chair conformation of this, which is hexane. So essentially, if you look at this here, it is like you're drawing, I guess I really can't do that tool here, but it's essentially, if you had the 3D version of this 2D hexane, if you looked at it from the side, so if you kind of flipped it and looked at the side, it would look like this. Because as we know, carbons are not simply linear. They're not 2D. So when they alternate going up, down, up, down, up, down. So basically, this hexane in 3D would look something more like this, which is the chair conformation, which took me a long time to understand. So let's kind of just get into how can we translate. So you might understand, okay, yeah, obviously I know this hexane, this is that, but how does that really look when we have constituents of the hexane that are not simply hydrogen? So let's say we have indicated stereochemistry. We have, there's a carbon, and let's just draw another carbon here. So you think, okay, well, there's a bunch of hydrogens, but now we have carbons. How do we draw that? So the easiest way to go about it, in my opinion, is numbering the 6 sides of the hexane. So let's do 1, 2, 3, 4, 5, 6. So now if you're numbering on here, there's not exactly a right way to number it, but this is how I've always done it. We do 1, 2, 3, 4, 5, 6. So continuing on with that, you might be thinking, well, how do I know this is a dash? How do I make the dash on here? So the main way I always thought about it is up wedge equals up and dash equals down. And I also should probably mention there are two types of when we're doing the chair conformation. There's two types of bond, or I guess just connections that you can make to the hexane. It's kind of hard to explain, but there is something called axial and equatorial. So axial, let's look at the first carbon of the chair conformation, which I have number 1. The axial would be going up. Oh, that's the wrong tool. Would be going up like that. While the equatorial would be going down to the side. The axial, you can think of it, the axial is straight up, it's going to be straight down. It's like an axis pretty much. It's just straight up, straight down. In this case, it is up. Equatorial, it is, if you think of an equator, it's not up and down, it's across a planet. So equatorial is to the side. So equatorial would be, let's just label A here. So this is A, and this here would be E. So this is equatorial. So this carbon that we have on number 1, it is on the dash. It would be, let's think, it's if wedge is up and dash is down, we have down because it's a dash. It would be on the equatorial. So we can just kind of assume CH3 would be here. Get rid of this 1 because it's a little confusing now. Or not, I guess it's not obeying what I'm trying to say. Let's get rid of that 1, it's a little cluttered. So the axial would just be H. So let's look at number 2. We have a wedge, so wedge would be up. So let's think about it. If axial was just up, now axial would be down on the next carbon. So that would mean equatorial would now be up. So let's draw it again. Oop, I'm just going to draw it with the pencil tool. Now we have CH3 here and H here. And also, little side note, when we have any big groups in the chair conformation, such as CH3 or anything bigger like ethyl groups or nitrogens or anything like that, we always think we want the big groups, like I just said, like the methyl, the ethyl, we want them to be on equatorial because equatorial is off to the side. It is not really involved with any steric hindrance. So in this case, this would be the most stable conformation, the most stable chair conformation here, because we have the methyl are equatorial, they're off to the side, they are more stable. So let us just, a little side note again, let's draw the chair flip version of this. So a lot of times you're going to be asked to draw the chair flip and the chair flip conformation of a certain molecule, and also asked, well, which one is more stable? So let's just do that right now. I've never been too good at drawing the flip, I'm going to be honest, but you're just going to have to bear with me. So if we flipped it here, let's just say it's that. Now, I always just do if 1, let's say 1 is here, this is 1. Now, on this one, this is 1. So we have 1, 2, 3, 4, 5, 6. And that would mean 1. When we do the chair flip, equatorial becomes axial, axial becomes equatorial. So we have equatorial here. Now this carbon would be, it would now be equatorial, or nope, it would now be axial down. So it would be looking like this. And then on the next one, it would be going up, and it would be axial. So we can just to make it a little simple, we have that. So in this conformation, we have CH3. Oh, that's the wrong tool again. CH3 here, and CH3. That's really small and hard to read, but CH3 is there. That's all you need to know. So if we know that, there we go. If we had a test question that was saying which one of these two conformations, this chair conformation and the chair flip conformation, which one's gonna be more stable, we can always say this one is more stable because this big group and this big group are equatorial. So that means they are more stable, they're further off to the side, they're not interacting with each other. But on the other hand, on the chair flip conformation, here and here, these are axial and they are closer to each other, the more proximal, I guess. So they are reacting with each other, they are involved with steric hindrance, and it makes it less stable. So this here is the more stable of the conformation. So after saying all that, I think I covered everything I wanted to talk about. Please let me know if I got anything wrong or made any simple mistakes, because I'm still an undergrad student. I do not know everything. But please comment if you have any requests or any additions to make. So thank you for watching.